Is it? Okay. So thank you. Welcome back. And before we begin, a couple of announcements. So the first one is there is Wi-Fi, and the username, the ID, and the password is on the blackboard, but it's also written in bigger capital letters on the bulletin board outside if you need it. And the second announcement is there is lunch available in the cafeteria. There are 2 lines, one to buy the ticket and one to actually get the food. So you might want to go there as soon as possible after the end of the talks of the morning session. And so our second speaker is Maicon Benvenutti from Unicamp, and he's going to talk about global nonlinear stability of steady solution of the 3D incompressible Euler equations with helical symmetry and no swirl.
Okay, thank you. First, I would like to thank the invitation to present my first international lecture. It's an honor for me to present at this school with so many excellent and famous mathematicians. Okay, this is a joint work with Professor Helena and Milton. In this work, we will show that we can extend some stability results for the 2-dimensional Euler equation made in this paper by Burton and also made in this paper by Wan and Benvenutti to the 3-dimensional Euler equation with helical symmetry and with an additional geometric constraint. In this article, Burton considered the 2-dimensional Euler equation in a bounded domain, and he proved that the extractive maximizer of energy restricted some isovertical surface are stationary solution to the vortices equation and also are stable in a non-linear sense. Here, we will prove that there exists a corresponding result for the helical case. Okay? Therefore, we will obtain some helical stationary vorticity to the 3-dimensional Euler equation. And in this article, Wan and Benvenutti proved a non-linear stability for circular vortex patch. And here we will show that there are some helical stationary vorticity which have the same stability property. Okay? And to obtain our result, an important step is to make a correct reduction by symmetry. In this paper, Ettinger and Chichi used the helical symmetry and the no swirl geometric constraint to rewrite the vorticity equation in a similar form to the 2-dimensional case, namely as a scalar transport equation without any stretching term. So here, we use the same reduction made in this paper. And then, we will adjust the Burton's technique and also the Wan and Benvenutti techniques for these formulations. Okay? In what follow, firstly, I will talk briefly about the reduction made in this paper, and then I will show how we adjust the Burton's technique for this formulation. Okay? Here you have some notations and definitions. For each fixed point x, we define this R as this parameterization of circle passing by x, and this S as this parameterization of vertical helix passing by x. We say that a domain omega is helical if it's invariant by these helices. Okay? And you say that a vector field U is helical if it satisfies these conditions. These conditions means that in cylindrical coordinates, the components of U are invariant by these helices. And finally, we say that a helical vector field is with no swirl if it's orthogonal to the helices. This is the tangent field to the helix. Okay? Here we have a draw illustrating a helical vector field with no swirl. Here we have a point x. This is the field in x, U of x, which is orthogonal to the helix. If you go to this helix until this arbitrary point xs by an angle ρ, we have that the field here is equal the field in the point x rotated by the same angle. Okay? And hereafter, we will consider the two-dimensional Euler equation in a helical domain. If this is a smooth solution for the Euler equation, then it can be proved that for each fixed ρ, we have that this is also a smooth solution. This result can be found in this Dutrefeuille paper. Okay? So using this property and the uniqueness of smooth solution for the Euler equation, we have that if a smooth initial condition is helical and with no swirl, so the solution remains helical and with no swirl over time. Furthermore, it can be shown that the vorticity has this specific form. And this third component of the vorticity satisfies this scalar transport equation. So we can use this equation to estimate this third component of the vorticity. And if you suppose that the helical domain omega is horizontally bounded, we can estimate this field. So, applying the Biot-Katumida theorem, we have that in this case, smooth helical solution with no swirl are global in time. Okay? All this result can be found in this Dutrefeuille article. So here we have the reduction proposed in the Ettinger and Chichi paper. We define this omega 0 as the omega restricted to the plane. And this Xi as the third component of the vorticity restricted to omega 0, and V as this transformation of the first two components of the velocity restricted to omega 0. Also, we can prove that the systems are completely defined by these variables. And also that they satisfy this system. Okay, eta 0 here is the normal field on the boundary of omega 0. Furthermore, if the domain is simply connected, we have the following coupling. For a fixed Xi, we have that V is the orthogonal gradient of G of Xi, where G of Xi is the solution of this elliptic equation, and L is this twisted divergent. Okay? To sum up, we obtain a system similar to the two-dimensional case. The difference between them is in the Biot-Savart law. While in the two-dimensional case, L, this L is the divergent. Here, L is this twisted divergent. So a question that naturally arises is whether the results made for the two-dimensional case can be adapted to this case. Ettinger and Chichi, in the article that I cited before, adapted the Udovich theorem. Namely, they proved the existence and the uniqueness of global solution for bounded initial conditions in bounded domain. Here, we adapt the Bertle and also the one equivalent result for these formulations. Okay? Here we have the definitions of weak solution. Hereafter, omega 0 will be a bounded, smooth, and simply connected domain. P a number greater than 4/3. And if Xi0 is a function in LP, we say that Xi in this space is a weak solution with initial condition Xi0 if they satisfy this equation for our test function. Yeah. Here, V is obtained by the previous Biot-Savart law. And the restriction in P is to ensure that this quantity is integrable. Okay? In our first result, we obtained some stationary solution for this equation. Note that a solution Xi is stationary if the divergent of Xi times V is 0. Okay? Okay, here you have our first result. And here we consider omega 0 as a circular domain in the plane, and we fix G a real monotonic function in LP. So we affirm that Xi defined in this way is a stationary solution. Our first observation is that by reverting the reduction made, we can interpret this result as this field being a stationary helical vorticity to the three-dimensional Euler equation. Okay? And all other results that will appear in this lecture can be interpreted in the same way, okay, by reverting the reduction made. In particular, if we choose G as a characteristic function on this interval, okay, we obtain this stationary vorticity. And we will show that the one equivalent stability can be extended for this stationary helical vorticity. In this sense, this field generalizes the circle vortex patch to the helical case. So in this lecture, we call this stationary vorticity as helical vortex patch. Okay? And the proof, let's do the proof. As we are in a circular domain, we can use the polar coordinates to rewrite this operator as this form, involving only the radial components. Remember that G of Xi is the solution of this elliptical system. So using this and this definition of Xi, we can obtain G of Xi explicitly by transforming this equation in an ordinary equation. So we can obtain V explicitly, and then we can compute divergence of V times Xi and show that it's 0. So Xi defined in this way is a stationary solution, and you have proved the first result. Okay, for the next result, we need some definitions. We define the energy associated with the system as this quantity. This quantity is formally equivalent to the integral of the velocity squared over a period of the helical domain omega. Other definition. We fix a function f in LP. So we say that a function G is a rearrangement of f if for our number beta, we have that the inverse images of this interval by F and by G have the same Lebesgue measure. Okay, other theorem. We fix F a function in LP, and we define this bold R as the set of R rearrangement of F, and we induce in this set the LP topology. So we affirm that the energy restricted to this set attain its supremum. And furthermore, if Xi is a local maximizer, then Xi is a stationary solution. Okay, in the proof of this theorem, we use optimization theory of convex functional obtained in this article, developed in this article by Bertel. In fact, usando the theory of this article, some property for G and the fact that the energy is defined in this way, we can prove that the energy attains its supremum on the set of rearrangement, and if Xi is a local maximizer, then there exists a real monotonic function phi where we have this equality. So using this equality, we can compute this and show that it's 0. Therefore, Xi is a stationary solution. Okay? Our next step is to prove the stability for these stationary solutions. Okay? But before we have a theorem of existence. Remember that in the Ettinger and Titi article that I mentioned before, proved the existence of a global solution for bounded initial condition. Here we have existence and uniqueness in the Ettinger and Titi article. Here we have existence of a global solution for an arbitrary initial condition in LP. Okay. One observation is that we have not proved uniqueness of solution. But it is in accordance with the two-dimensional case, where the uniqueness in LP for P different from infinite is an open problem also. Okay? Now we have the Bertel's result for the helical case. 5? Oh my God. Okay. We suppose that C0 is a strict maximizer of the energy on the set of our rearrangement. So we affirm that C0 is a stable state solution. More precisely, if C is a solution such that the initial condition is closed from C0, then the solution remains closed from C0 all the time. Okay? I don't have more time, so I will not present the proof of this theorem. But the basic idea is to take a perturbation and transport the stationary solution over the velocity associated with the perturbation, and make some estimatives and use that the energy is a conserved quantity. Okay. Use Di Perna-Lyon's theory for rearrangement of scalar transport equation. Okay. And here we have the same result for this stationary solution that we obtained in the first theorem. Okay. The proof is similar. The difference is that here we use the moment of inertia as a stationary, as a conserved quantity. And finally, we have the one equivalent result for the helical case. Okay. here we have the L1 stability for this stationary solution under perturbations such that the initial conditions are also characteristic function. The demonstration of this theorem is more straightforward and also use that the moment of inertia is a conserved quantity. Okay, thank you very much.